get things started. So it's day 90 of 100 Days of About, and today I'm going to be reading MobileNet V2 and MnasNet, just to get a kind of like a precursor understanding to EfficientNet. And I'll also be going over the introduction for EfficientNet and the related works section. So I'm going to start with that, and then what I'll do is go ahead and get MobileNet and MnasNet into my iPad, the papers into my iPad. But I'm just going to go over maybe like the blog for both of these models and try to get an understanding of what the actual inverted rectified linear Conv block is. So I'm going to go ahead and open up EfficientNet on my iPad. EfficientNet. Okay, there we go. So I'm going to go ahead and read intro and related work. So I'm going to put it over here and get started. All right, so let's talk about the introduction. So first things first, what they say is the fact that scaling up any ComNet makes it achieve better accuracy, and it's a common widely used tactic to achieve better accuracy and better performance for any single model. But there's an extent to which you can just arbitrarily increase the the content and expect it to do better just because of the fact that it's eventually going to overfit. So yeah, they say that scaling this process of scaling is not really well understood, and although that there are ways to do it, one of the ways is to just commonly scale one of the three dimensions, which is width, depth, and image size, which is represented by image resolution. But this scaling is technically done by manual tuning, and it's pretty tedious and inefficient, and leads to like suboptimal accuracies or efficiencies. So what they propose in this paper is a solution to this problem where they develop a compound scaling method to uniformly scale an arbitrary baseline model. And so they point to this figure where we can see a baseline model. We can see a model where only width is scaled, only depth is scaled, only resolution is scaled. And whereas compound scaling takes into a common ratio of all of these coefficients and scales them uniformly. And what they say is that it intuitively makes sense because of the fact that, if you have a higher resolution image, your network also has to have more layers, and due to the fact that it's going to be a better, highly dense input, there's more like input to work with. And they also refer to the fact that there's some sort of relationship between the width and depth, although it's not really explored completely. And finally, they just talk about their results and what they get, and how it's performing at a state-of-the-art level using their baseline architecture called efficient nets. Okay, next up, gonna read related works. right? So, three things discussed in this section: accuracy, efficiency, and model scaling, which is the final conclusion here. So first of all, ConvNet accuracy, and it talks about the history of ImageNet competitions, where starting with AlexNet, which won 2012, later on GoogleNet with 6.8 million parameters, winning 2014, and then SENet in 2017 with 145 million parameters, and then so on with 557 million parameters. So you can see that gradually the increasing of the model scaling is occurring over the years to achieve better accuracy. And it's going at a steady rate. You can see 6.8, 145, and then 557. But eventually we hit a cap on the hardware limit where we can't just arbitrarily increase the model depth and expect it to do better because of the fact that it might be much harder to train it. So what we actually need is better efficiency in the model. So efficiency can be talked about in different ways, and they introduce the fact that there's model compression, which is one common way of increasing the efficiency, and also allows it to run on mobile devices and devices which don't have very strong processing units. So these ConvNets like MobileNet and SqueezeNet, all of these models are able to run efficiently on smaller processing units. However, what they want to do here is to increase the efficiency of these state-of-the-art models, which are doing really well with these huge 145 million parameters. So to achieve this goal, what they resort to is model scaling, uniform model scaling, which they propose in this paper. And yeah, the final section just talks about the process of scaling a model, where giving an example that ResNet can either be scaled down or up by adjusting the depth, and other architectures like wide ResNet can be scaled using the width, the number of channels. And of course, increasing the image input size will also increase the overhead floating point operations per second. So the question here is how to efficiently scale all of these metrics with depth and resolutions while keeping the model efficient while scaling it. That's the entire question here. I think one thing that I want to get cleared up is what exactly is a width? Yeah. So I guess width is the layer, the dimensionality. Is that what I'm getting to here? Oh my gosh. Specifying the depth. Okay. And the channel here would be the amount of colors, where 3 channels would be red, green, and blue. But if we increase the number of channels, we can have more colors, I guess, and lead to better analysis due to the fact that we are able to section it into more colors, leading to more information learned. Okay. Now still doesn't answer the MB-conv block that they're using here, which is in MobileNet. So let's check out MobileNet. Let's read the blog first. When did this come out? 2017. I want to know how it is implemented. Oh, hi there. Okay, it's talking about the linear bottlenecks between the layers and the shortcut connections between the bottlenecks, but I don't see where. There's no in-depth description, so I might as well just check out the paper. There we go. This whole section about linear bottlenecks. Gosh. Yeah, I just got a message here. Have you heard about Tidy Tuesday Data Analysis Series by David Robinson and Hoping? if it was possible to do all of it in Python instead of R. I don't think I've heard of it, but okay. Essentially, if it's possible to code it in R, then it's possible to put it in Python because Python's just a higher level language than R, and there's a lot of libraries that help Python do a lot of things. So what you could do is search up whatever is being implemented using R on Python, look at the libraries maybe for these things, and then check it out. But I would say yes, although I don't necessarily know what tidy to say data analysis is. But my recommendation for data analysis using Python would be checking out tools like Pandas, NumPy, scikit-learn, and all of those tools and libraries. Usually they have everything that you really need for data analysis. Okay, so I guess here we can see the compilation of the residual bottleneck block, and this is kind of what I need to do. Where I'm not sure what this dwise is. Dwise TensorFlow, maybe. Let's check that out. So depth-wise convolution 2D block. Okay, that's what it means, and it might be a depth scaling, and that might be what it's talking about here. I think it would be a good idea to actually read this entire paper now that I think about it. Oh shoot, it's pretty long. Okay, I'll add this to what is this here? It's the entire architecture. A couple of bottlenecks where the bottleneck is defined over here using 1x1 Conv2v using relu and 3x3 dwise, and I think dwise means depth-wise convolution and block, also using relu activation, and a linear Conv2v 2D. So something that might be good is to just start by implementing this section here and then continuing with EfficientNet. Okay, let's do that. Tomorrow I have my final, so I'm going to take things pretty light for tomorrow. What I'll end up doing is something very easy. Day 91. I'm going to conclude things here. So what I'll do is read MobileNetV2. What I ended up doing today was actually reading these MB conv blocks, those inverted residual net convolutions. I'll leave it like this. Okay, anyways. And then I'll edit that later. We will. So basically, what is this? The bottleneck, sorry, wrong paper, bottleneck residual block. RDYs, layers. So these are the questions I want to answer for tomorrow. And yeah, that'll be it for today. I'll be back tomorrow to continue things.